Well, I am not Sean, but I was supposed to go after him. So good morning, everyone. Thank you, thank you. So today I'll be speaking to you about asynchronous backing. It's the new feature of Polkadot, which delivers shorter parachain block times and an order of magnitude increase in the quantity of Polkadot block space. So let's dive into it. So first, an overview. We're going to touch on what synchronous versus asynchronous means in this context, why asynchronous backing is desirable. We're going to discuss high-level mechanisms of asynchronous backing. Then these storage structures, both in the parachain runtime and in the relay chain client, called the unincluded segment and prospective parachains. These are all important to how async backing functions. Finally, we're going to discuss how async backing enables some other Polkadot roadmap items. All right, so first we're going to touch on synchronous backing. That is the current form of backing that's running on Polkadot. We have two basic processes. We have collation generation and backing, which is coallators on the parachain side creating parachain blocks, sending them up to a backing group as collations, backers providing backing statements after re-executing those blocks. So all of that happens on one side here, and you can see that after all this is done, our white arrow on the bottom shows that parachain block in is ready for availability at that point. It becomes backed on chain, and then the availability and inclusion step starts, where we are spreading out those proof of validity chunks amongst the validator set, and then bringing in bit fields to place on chain, and finally include a parachain block in the relay chain. Now, parachain block in +1 is built using parachain block in as it's seen included in a new relay chain block. And the result of this is that these two processes, these two purple circles here, are joined at the hip. Like one cannot begin until the other ends. And this causes some bottlenecks. So why am I not showing approvals, disputes, and finality in this diagram? So they actually don't gate the production of farther candidates. We only wait until a block is included, not until it's finalized, to produce a new parachain block on top of it. So that's why I'm focusing just on these initial steps. Yeah, so I touched on this, but why is this synchronous? Again, it's because the availability and inclusion steps and the collation generation and backing steps, they require one to finish before the other can start. There aren't two separate processes that can run in parallel here. All right, so now we're going to look at asynchronous backing in a simplified version and how that is different. So our white arrow here represents execution. This is just a loop of execution that's running. Collators they have their own notion of slots for producing blocks now, and rather than triggering the production of a block whenever a relay chain block has included a previous candidate from that parachain, instead they trigger the building of blocks on a sort of a routine schedule. And so we're building those blocks. Again, we're passing them up to backers in the form of collations. They're receiving backing statements. But instead of immediately, say, backing the blocks that are produced here on chain, instead we cache those candidates in a storage structure in the relay chain client. So we're accessing data to write these candidates to storage essentially, and later those candidates are then used for the availability and inclusion step. So we're going to read those cached items in order to, say, back a candidate later on chain, and this is effectively decoupling the collation generation and backing step from the availability and inclusion step. Like we can build up a stockpile of these candidates, and we are pushing candidates to that stockpile from the collation generation and backing process, then pulling them from our stockpile for the availability and inclusion process. Now, on the other side, we have sort of another stockpile going on, which is actually located on chain. These are included parachain blocks and relay chain info that are effectively cached on chain. So those were already available for collation generation and backing, but we're adding this new structure of cached pair block candidates on the bottom in green. That's kind of our new structure here that we're adding that enables us to separate these two processes, these two white arrows of execution. Yeah, and as I got at, essentially these are two processes that can run in parallel. There's a certain degree to which one has to depend on the other. Of course, if we stopped including blocks for quite a while, then we wouldn't want to just keep building up this longer and longer cache of unincluded candidates. So eventually collation generation and backing needs to halt based on that. But to some extent, they are decoupled, and this gives us a bunch of advantages. So we make some assumptions in order to enable this caching of candidates, and we build on top of candidates that have not yet been included. So to make those assumptions, or rather the assumptions we're making, one, the best existing pair block I'm aware of will eventually be included in the relay chain. This is something that a collator is assuming. To an extent, it's something that a backer is assuming when they back candidates within async backing. So this is not always true, but I'll get to why that's not a problem. And number two, there won't be a chain reversion impacting this best parachain block. So even if it gets included, we won't have a reversion that impacts it. And if those two things are true, then async backing runs without a hitch, and there's no wasted effort, and we're effectively able to predict the future of the chain to an extent in order to begin further work early. I should highlight here that the stakes are very low. The worst case here is that a block that we expected to be included doesn't get included. Maybe we have to remake a few blocks. Like, it's really not a big deal if these assumptions fail temporarily. So we can afford to make these assumptions, and what they give us is much more important than what they could take away. So what are the advantages of async backing? Why should we care about this? It allows us to get 3 to 5 times more extrinsics per block. And that's because collators have more time in which to fill each block. So rather than about a half a second to fill a block with transactions, collators have 2 seconds to fill each block. And then we get shorter parachain block times. We get 6-second parachain blocks rather than 12-second parachain blocks. This is because advanced work ensures that backable candidates for each parachain are present to be backed on the relay chain every 6 seconds, which was not the case with synchronous backing. And we'll get into why in a little bit. Now, this results in a multiplying those numbers together, you could see like double the number of blocks, roughly 3 to 5 times the extrinsics per block. We're getting a 6 to 10x boost in the amount of throughput from Polkadot parachains overall. And there are actually fewer wasted parachain blocks as well, because previously, if the relay chain block on which a parachain block was based became stale for some reason, that parachain block didn't make it onto the relay chain in a timely fashion, previously we would need to throw that parachain block away because you were only allowed to place parachain blocks on chain that descended from the most recent relay chain block. Now we can have sort of a longer notion of ancestry. We can relax that requirement. All right, so how are we doubling the rate at which we include parachain blocks from 12 seconds to 6 seconds. This is most obviously visualized in this pipelining diagram. So we're going to start on the left with our purple section. This is with synchronous backing, so no parachain block pipelining. We have parachain block candidates 1, 2, 3, and 4, and we have relay chain blocks 100 through 103. You can see that one candidate needs to be backed and included before we can back the next candidate from a single parachain, that is. And with asynchronous backing, we get this nice pipelining where we have a backed candidate available to include every single block, and we can actually back candidate n+1 during the same block that we include candidate n. So that results in double the rate of parachain blocks being backed and included, because we can essentially start that work early for later blocks. Now, to take another slightly deeper look at synchronous backing, we have collation generation that's happening on the far left of this diagram, where collations, new parachain blocks, are generated. Then the collator protocol submits that collation to a backing group on the relay chain. Then we have our backing process, which is off-chain. So this is backers making backing statements, and then once a cohort of backers have met the backing threshold for a candidate, then they communicate that candidate to the rest of the Polkadot validator set, so that a block author can then mark a candidate as backed in a relay chain block. So all of that is happening off-chain. It's producing this stream of backable candidates, and in synchronous backing, we take those candidates and we directly just back them on-chain. All of this, from generating the collation until backing a candidate on-chain, all that needs to take place within 6 seconds. Reason being, if it doesn't take place within 6 seconds, then we essentially miss our timing, and then a parachain block would only happen every 18 seconds rather than every 12 seconds. So it's kind of like a starting gun. When one parachain block candidate is included on the relay chain, that's the starting gun to start producing the next candidate, and you only have 6 seconds to get it backed. That condensed timeline is a part of the reason why why collators previously only had about half a second to try and fill their blocks with transactions. They were just in a time crunch. All right, so adding more to our diagram here, in the second relay block, since the last included parachain block, we get erasure coding in the availability process, and bit fields being collected by a block author, being placed on chain, and eventually a candidate being included. So that's, well, these two processes occurring during two different relay chain blocks, those make up the total 12-second timeline of synchronous backing for a parachain block. And when looking at building new parachain blocks, collators will watch the stream of new relay chain blocks. So this is kind of a feedback loop where the newly included parachain blocks are fed back into the start of the process again, providing this notion of a new best head, otherwise called a latest included parablock on this diagram, and some other validation data. So essentially the cycle restarts every 12 seconds. So how is this different with asynchronous backing? So we're going to start by describing, again, from collation generation. So we produce our candidates just like we were. We submit them to a backing group just like we were. And then the off-chain backing process happens. But rather than submitting those backable parachain block candidates directly on-chain and backing them on-chain, we instead cache them in this block of, or this cache of parachain block candidates called prospective parachains. These are parachains that could exist in the future, or rather, I guess, additions to parachains that could exist in the future if they happen to be included in the Polkadot relay chain. So you'll notice that our collation generation and backing process here, I did not have any notation signaling that this was during some relay chain block timing. That's because backing is asynchronous. It is its own process. It's happening on its own schedule. But we still have this availability and inclusion step, which is sort of timed by relay chain blocks. So parachain block in is included, and parachain block in +1 is backed in the same block. So this backing on-chain step, and then erasure coding and this including on-chain step, they're happening for different parachain blocks from the same parachain at the same time. And again, we have this feedback mechanism where new relay blocks are kind of scraped by collators. Collators see those, pull them off chain, and they don't necessarily use those relay blocks while they're fresh, or they don't have to. And then also the collator is now generating its own notion of candidates to build on top of, called the unincluded segment. We will get into exactly what that is just now. All right, so the unincluded segment. This is one of our new data structures, one of our new sort of caches that is informing asynchronous backing. It is a parachain's record of all the parachain blocks on a particular chain fork that have been produced but not yet included. That is, they've been produced by a collator, communicated to a backing group, but they have not been included on chain. Now, this unincluded segment is used to apply limitations when constructing future blocks. One example of such a limitation would be with upward messages that a parachain is passing to the relay chain. If we exceeded some maximum message queue length, then the relay chain would start dropping any additional messages that we try to send to it. So as a parachain, we want to be conservative, and we want to make sure that we don't send so many messages so quickly that they start being dropped. Now, if you're building multiple blocks on top of each other, which have not been seen and included on the relay chain, then we have to do some of the bookkeeping ourselves as collators, and actually backers need to do some of this bookkeeping off-chain as well to make sure that we are not exceeding, for instance, queue sizes. And the unincluded segment lives in the parachain runtime. So each unincluded segment then is from the perspective of a particular parachain fork, because each runtime is only aware of one fork of the chain. And in this sense, the unincluded segment is viewed from the perspective of a new parachain block that is under construction. And that new parachain block is at the head of its particular fork in the runtime. So we're going to go through some visuals for trying to make sense of the unincluded segment. So we see on the far left here this gold item. It's the last included parachain block. It is not a part of the unincluded segment. What the last included parachain block gives us is we can see, for instance, how much unfilled queue length is there for messages we're passing upwards. That example of a limitation that we need to make sure to fall within. Our last included parachain block gives us a sort of a base state for that limitation, like how much queue length is left. Then we have our blocks in an unincluded segment. They're called ancestors because, again, we're looking at these from the perspective of a new candidate being built. So we would have our most recent ancestor, ancestor 0, and then some number of ancestors after it, usually a pretty low number in the unincluded segment. Each of those would have, say, a message count for upward message passing, and then we have another entity called the segment tracker, which essentially sums up all of these various resources that are being used by parachain blocks. Upward message queue capacity being an example of one of those resources that needs to be tracked. Let's see. Yeah, so the unincluded segment is added to as each new block is imported into the parachain runtime, and the unincluded segment shrinks when one of its ancestor blocks becomes included. And the maximum unincluded segment capacity is set both on the parachain and the relay chain. On the parachain, it would cause collators to, in the runtime enforces this. If you're exceeding your unincluded segment capacity by running a parachain block, your runtime will simply abort. Like it will choose not to execute that block because it knows it would be going over its limits. The backer, like the backing group you would submit this parachain block candidate to would not accept the block anyways because they know it's going over the limit. We have a question?
Essentially, does that mean that the parachain then stalls, or what is the degradation mechanism?
So in this case, it would be, yeah, so imagine for some reason the relay chain stops including blocks from your parachain. You're kind of stuck as a parachain block producer, as a collator, right? Like you need the relay chain to continue progressing at some rate in order for you to continue progressing. And so this was kind of strictly true in the case of synchronous backing. Like if the relay chain stopped producing or stopped including candidates, then your block production would stop immediately. And now it's kind of loosely true. Like if your unincluded segment is not already full, then you maybe keep producing blocks until you fill it up. But then at some point, because we don't want to run way too far ahead of the relay chain, we stop. So yeah, it's kind of a feedback mechanism that would halt a parachain, but it doesn't make anything worse.
Got it. And one more question. And so, from the end user perspective, what does that look like? Like, let's say when the relay chain stops, actually using the collators, or the collators just kind of stop working. Does that mean that there's like some kind of signaling, or what happens?
From an end user perspective, to
Yeah,
my
like
knowledge, like if
there's
the
like a
relay,
DApp. If there's a DApp, and the DApp is submitting transactions to the parachain, will they just won't go through, or
I
what
think that
happens?
would just look like you try to post a transaction and then
It's a failed
it just
transaction.
doesn't finalize, or it
Okay.
isn't even included for a really long time. That's probably what you would see from an end user perspective. I think it might be nice to give end users more notification of exactly what's going on and why there are delays. But I haven't seen any UI that ever did that.
Got it. Okay. Thank you.
All right, we have another question on the far left here. And you're welcome.
Yeah, hello. Yeah, so my question is on because, for example, the blocks are not yet included,
Yeah.
and each consecutive block is its own fork, right? If you're building on an included block, it means in the parachain perspective, you are producing more forks of a block of a parachain, right?
Yes, so if you're building, say, multiple candidates that don't descend from each other, that are all built on top of the most recently included parachain block, if you're building, say, several candidates in several different parachain runtimes, then yes, those would all be sort of their own forks. And that's a good point. There are multiple unincluded segments per parachain at any given moment. Each unincluded segment corresponds to a different fork of the parachain. Those forks might not yet be represented on the relay chain because, again, these parachain blocks are not included yet.
Yeah, so but then what if it's one parachain and its previous block is not yet included, and now it's producing new block and submitting it, right? So it won't wait until it is included. Yeah, there's backing included. Yeah, it won't wait until it's included. It will continue building new candidates.
Yeah.
The same. I'm not talking about different parachain. Just let's say parachain A, right? It's building one block, second block, but the second block is a candidate because the first block wasn't included, right?
Yeah, yeah.
So the following blocks will be also a forks, right? And not because it won't if the previous block won't be included ever, it means it has to reorg or maybe choose another fork. So it means even in a parachain perspective, yes, single parachain to be a fork, right?
So I believe that if each block in the unincluded segment descends from its ancestor, so if we have, say, our last included block is ancestor 3, but then ancestors 2, 1, and 0 all sort of descend from each other in a chain, then what we get is a single parachain fork. And then if for some reason, say there's another fork of the parachain, another potential candidate, say if we had ancestor 2A and then like a 2B, for instance, and then 2B is the one that actually gets included on the relay chain, then this whole unincluded segment, ancestors 2, 1, 0, those would all be thrown out as essentially the fork that's behind finality.
So now the collector will have to build a new block again.
Yes, and that's the so like the stakes are pretty low, but those are the stakes. We're making some assumptions about what will happen in the future with the Polkadot relay chain, and we do have to repeat some processing if that ends up being wrong.
Okay, thank you.
Just one last question because it made me think about what he was saying. So again, if that happens, where essentially, would it be that the coalers and essentially have to resend these blocks again, like they have a cache? Is that what happens, or like all the transactions get thrown out and then reverted, quote unquote?
So imagine some other block, like rather than ancestor 2, we get 2A. Some other candidate is the one that becomes the next included block for a parachain. Like there's no way that we can actually reuse ancestors 1 and 0, right? Because they descend from ancestor 2, not from ancestor 2A. So like the hashes don't line up. Even if those transactions are still valid, like you're not enacting them on top of the same state that's expected. So we do kind of always have to throw those out and redo that work. That's why we really you can get all the benefits of asynchronous backing from basically having a maximum unincluded segment length of something like 2 or 3. So we never let this chain of candidates get too long, because as you extend the length of that chain of candidates, the costs of being wrong in your predictions with async backing grow.
Got it. So it's kind of like the transactions are reverted, quote unquote.
Yeah,
right?
yeah, in a sense.
Interesting. So I'm just curious, is there like a mechanism to, I guess, signal, maybe with Polkadot.js that this happened?
I think so really at the moment, this kind of falls within the normal fork selection and fork choice and dumping of non-preferred forks. I think it's all handled by the same mechanism on the parachain side. So it pretty much looks the same as having two different forks of your parachain that are on two different forks of the relay chain. It looks the same from the parachain perspective as that, and so we can kind of use the same rules to recover if we were on what becomes a non-preferred fork.
Got it. Because this could happen into the future, right? Like the end user could think that the transaction went through, but then a few seconds later or something, then
Yeah. I guess it's very similar to if you're on two different forks of the relay chain, and then I don't know, there's a dispute or another fork happens to grow longer than your fork. That fork choice change it kind of has the same impact whether you're looking at blocks that are a part of an unincluded segment or blocks that were already included.
got it. Thank you very much.
Yeah, welcome. All right. So moving forward here, we're going to add a little bit more detail on some of the other contents of ancestors that are kept track of in the unincluded segment. So the UMP message count that we were showing on the blocks in the top of our visualization, that's actually a part of a larger field called used bandwidth that covers things like UMP message count, UMP total bytes, and also HRMP outgoing, which covers all of your different HRMP channels from one parachain to other parachains. This is again horizontal message passing. So this is if you want to message other parachains, you have separate queues for each of those channels. And so we're keeping track of sort of our outgoing queue capacity for each of those channels. We also have things like an HRMP watermark, which is actually only kept track of in the unincluded segment tracker, and this notion of a consumed go-ahead signal, which if you remember from my Cumulus lecture, a go-ahead signal is when the relay chain via the parachain validation function pre-checking process, when you are trying to upgrade your parachain code, a go-ahead signal is when the relay chain signals back down to your parachain that, yes, this code can compile and we have approved it. That's when a parachain would update its state transition function. So a bunch of these different things are being kept track of, both in the ancestors themselves within an unincluded segment, and then also in this segment tracker, which tracks sort of all of this resource use overall. All right, so there is another big data structure involved here that I should also cover. This is called prospective parachains. It is a relay chain's record of all unincluded candidates on all chain forks from all parachains. So as you can imagine, that ends up being a pretty contorted data structure. So it's as if you folded all the unincluded segments into one giant structure. So it's used to store candidates and later provide them to the on-chain backing process. And this lives in the relay chain client. So it lives off-chain. That's why it needs to be aware of different forks consciously, because if you're in a runtime on the relay chain, your perspective is limited to a single fork of the relay chain, but not so in this case. So I have some diagrams to try to show what an example of prospective parachains might look like. So prospective parachains contains a bunch of these structures called fragment trees. Each fragment tree is composed of multiple unincluded segments for the same parachain. And fragment trees are rooted in the relay chain at active leaves. So if we're going to look first at the top left of this diagram, we have our relay chain. We have a finalized head. This is the most recent finalized block on the relay chain in gold. And then we have a couple active leaves. These are blocks 2A and 3. These are the only two blocks. These two green blocks are the only ones that we would build out fragment trees for, which again are keeping track of unincluded segments for parachains. And to cover again what an active leaf is, for instance, 2B, block 2B on the relay chain would not be an active leaf because it's not a leaf. And block 1B on the relay chain here is not an active leaf because it is behind finality. It does not descend from the finalized block. All right, so fragment trees are built per scheduled parachain at each leaf. So if a parachain is unscheduled, that is, if there's no execution core on Polkadot that is assigned to that parachain, we don't need to keep track of candidates for that parachain because we're not going to be including any of them on the relay chain very soon. So in this case, we have 3 parachains in our little example setup here. Their IDs are 2000, 2001, and 2002. Now, 2000 is only assigned an execution core at relay block 2A. 2001 has no cores assigned, so we won't see any fragment trees corresponding to it. And then 2002 has a core assigned to it at both leaves, both 2A and 3 on the relay chain. So this results in 3 different fragment trees, 1 for parachain 2000 and 2 for parachain 2002. Now, fragment trees can have 0 or more fragments representing potential parachain blocks making up possible futures for that parachain's state. And for each of these fragments that shows up in a fragment tree, these are, again, parachain block candidates. Collation generation, the passing of that collation to a backing group, and seconding work, which is at least one backer checking and approving of a candidate. All of that needs to have taken place before any candidate can show up as a fragment in a fragment tree. But then we sort of decide at that point that these are worth keeping track of. So to look at our mock fragment trees here, we have for leaf 2A, parachain ID 2000 on the left. This fragment tree contains a single candidate. It would represent a single unincluded segment of length 1. So on the parachain side, you could imagine that this is an unincluded, this parachain doesn't seem to have any forks here, no forks that are unincluded at least. So it just has one fork with a single candidate on it. And then we have a fragment tree that's empty, actually, for leaf 2A, parachain ID 2002. That would be, the collators have not produced and communicated any candidates that are ahead of inclusion. So the last parachain block that was generated and communicated to backers for that parachain based on that relay leaf is already included on the relay chain. And finally, we get to see kind of the tree structure in this fragment tree 3. So it's on relay leaf 3 with parachain ID 2002, and you can see that there are kind of multiple unincluded segments that are represented in this fragment tree. Candidate 1B would represent an unincluded segment of length 1, and candidates 1A and 2 would be on an unincluded segment of length 2. So again, this is our snapshot of how the relay chain keeps track of these candidates that are not yet included, and how it's going to store those and later make them accessible for on-chain backing. All right, so looking back at kind of this first diagram of asynchronous backing, we've now seen how we've introduced some new data structures that allow us to separate the collation generation and backing phase from the availability and inclusion phase. These cached parablock candidates, but now in this diagram, which structure did I leave out the name of for simplicity or to add clarity? All right, I see no hands raised, so I'll move forward. That is prospective parachains. That is our bottom green element here, cached parablock candidates. That is our prospective parachains, our fragment trees. And then which structure did I omit entirely from this diagram? That would be the unincluded segments on parachains, which if I were to include them in this diagram, it would be kind of as an additional green data element next to the top green element. Those included parablock and relay info that are cached on-chain. There's additional information in the unincluded segments that are on parachains within their runtimes. So that's kind of how we have additional data structures that we've created that allow us to decouple these two processes. And finally, what can asynchronous backing allow us to do in the future? One of the most important things and most exciting things is exotic core scheduling. So imagine here that every color represents a parachain's execution, and we are visualizing 4 cores through time and which parachains they are assigned to. So you can see, for instance, that the orange parachain has many cores assigned to it, and that's what we would call, or it has many cores assigned to it, say at block 2, maybe relay block 2 here in our diagram. And that's possible due to something called exotic core scheduling. Exotic core scheduling encompasses a few things. It's multiple cores per parachain per relay chain block. It's overlapping leases of many lengths, which allocate that block space. And also it's leases coinciding with on-demand usage in order to provide sort of spikes of throughput when needed. But how does asynchronous backing help with this? Well, in order to build 2 or more parachain blocks in a single relay chain block, we actually need the unincluded segment, and we need prospective parachains. Again, these structures are keeping track of sort of dependencies that we need to satisfy in order to build one block on top of another. And without that notion of dependencies, we could never build 2 parachain blocks within a single relay chain block. So yeah, asynchronous backing laid the groundwork for sort of unbounded parachain throughput, at least as far as we can assign many, many cores to them. All right, so if you want to read farther into this, so we have some rather chunky PRs, both on the Polkadot and Cumulus side for async backing. And then we also have our Polkadot parachain host implementers guide, and a particular section called prospective parachains, which describes in more depth what I was trying to get across about the way Polkadot validators store these future parachain block candidates. All right, do we have any more questions? No more. Awesome. Well, thank you all.